I need to tell you about what just happened with this interstellar comet, and honestly, I'm still trying to wrap my head around it. So NASA dropped new observations today, and the first thing that went through my mind when I saw them was the same thing everyone else is saying. This doesn't even look like the same object anymore. Like, we've been watching this thing for weeks now. We've seen it do all kinds of wild stuff, flaring up, calming down, shooting off jets in different directions, getting brighter, then dimmer, then brighter again. We've watched its rotation change. We've seen the coma hollow out and then fill back in. This comet has been putting on a show, and we thought we'd seen most of what it could do. But what came out today isn't just another phase of activity. It's not just a continuation of what we've been seeing. This is something fundamentally different. The comet literally looks different. Not metaphorically, not in some abstract scientific way. I mean, if you put the images from a few days ago next to the ones from today, you would think you're looking at two completely different objects. Before we continue, if this has your attention, you can subscribe, turn on notifications, and hit like anytime. And for the best viewing, switch to full screen and enjoy what's coming next. Let me walk you through what we're actually seeing here, because this is important and it's moving fast. The new batch of data isn't just one nice picture that someone took through a telescope. This is a coordinated observing campaign. We've got visible light images, infrared data, polarization maps that tell us how the dust particles are scattering sunlight, spectroscopic data breaking down the chemistry. All of these different instruments and wavelengths pointed at the same target during the same observing windows. And when the team started lining all of this up and comparing it to what we had from just last week, the reaction was pretty much universal confusion. People were literally asking, what happened to our comet? Where did it go? Because what we're seeing now doesn't match what was there before. Let's start with the most obvious change, the one you can see even if you're not a scientist. The shape has completely transformed. In the earlier images, the coma had this classic comet look. You know what I'm talking about. That teardrop shape, bright central region where the nucleus is hiding, then this soft glowing cloud around it, and then the tail peeling away in one dominant direction, flowing smoothly behind it as the comet moves through space. That's what comets are supposed to look like. That's what this one looked like a week ago. In today's high contrast images, that shape is gone. The inner coma isn't teardrop-shaped anymore. It's stretched. The bright core region, instead of being round or slightly oval, is now elongated along one axis. It almost looks like someone grabbed it from both ends and pulled. Some people are describing it as looking like a tiny bar hiding inside all the fuzz. And the tail, instead of flowing smoothly out from this stretched core, seems to split. It forms this shallow V shape instead of a single coherent stream. If you put yesterday's images and today's images side by side, it's like looking at two different comets. The old version looks like a rounded lantern, soft and glowing. The new version looks like a glowing spearhead, sharp and elongated and aggressive looking. That's already bizarre, right? A comet doesn't just change its fundamental shape in a matter of days. But here's where it gets even weirder. When you change filters and look at different wavelengths, the differences get even more dramatic. In visible light, the comet used to have this pretty steady color, mostly greenish-white, which is exactly what you'd expect from a mix of gas and dust. Gas molecules fluorescing in sunlight, dust reflecting it, all blending together into that characteristic comet glow. But now, in these new observations, the color profile has shifted. The inner region, that stretched core area, looks whiter and harsher, almost stark. Meanwhile, the outer halo, the more diffuse part of the coma, has taken on a slightly redder tint. Now switch to infrared and the pattern flips. In infrared, we're looking at heat. We're seeing how warm different parts of the coma are, which tells us about the size and composition of the dust particles. In this new data, the outer coma is showing up hotter and brighter than it should be. Meanwhile, the inner region isn't dominating the infrared signal the way it used to. Put all of this together, visible light and infrared and everything in between, and the message becomes crystal clear. The way this comet reflects and emits light has fundamentally changed. That's not a subtle thing. That's not just a matter of slightly different viewing angles or the sun hitting it differently. This means the actual material around the nucleus, the dust and gas mixture that makes up the coma, has changed its composition and structure. The polarization maps make this even more obvious, and honestly, this is where it gets really interesting from a scientific standpoint.
Polarization measures how aligned scattered light is, and that tells you about the physical properties of whatever is doing the scattering. Dust grains, the size of the particles, their shape, how they're oriented, whether they're fluffy or compact. In last week's data, the polarization pattern was straightforward. Stronger polarization along the edges of the coma, weaker near the center. That's standard comet behavior. It's what you get when you have a mix of fine dust particles, more or less evenly distributed as you move away from the nucleus. But in today's data, that pattern is completely broken. There's this band of unusually high polarization cutting across one side of the coma, almost like a stripe. And on the opposite side, the polarization drops below what any of the models predicted. What does that mean in practical terms? It means one side of this comet is now dominated by a completely different type of dust than the other side. Maybe larger, more compact chunks being ejected in one direction and finer, fluffier material going the opposite way. The comet is not shedding material uniformly. It's throwing different stuff off different sides of itself. So when you add it all up, visually, structurally, and physically, this thing looks like a different comet. Not because it actually is a different comet, obviously. It's the same nucleus, same chunk of ice and rock that came from another star system, but it's shedding different layers than it was shedding before. We're seeing deeper into its structure. We're watching material that was locked away inside this thing for who knows how long, and then immediately starts sublimating and blasting off into space. And here's the really important part, the piece that ties all of this together, the timing. If you take all these observations, the spacing of the new tail branches, the elongation of the core, the shifts in the polarization pattern, the changes in color and temperature, if you work backwards from all of that and try to figure out when this transformation actually started, you get an answer that's kind of shocking. It wasn't weeks ago. It wasn't a gradual process that we just failed to notice. This happened in days. Somewhere between the last observing session and this one, something changed inside the nucleus. A new layer became active. Think about what that means. This comet has been cruising through the solar system for months now. It's been getting closer to the sun, heating up, becoming more active. We've been watching layer after layer of surface ice sublimate, but all of those earlier layers were relatively similar to each other. They produced similar colors, similar dust distributions, similar activity patterns. But now, apparently, we've burned through all of that outer material and hit something different, deeper, older material, stuff that's been locked away since this comet formed in orbit around another star, probably billions of years ago. And that material is now being exposed to sunlight and blasted off into space, mixing with all of the debris from previous outbursts. That explains everything we're seeing. It explains why the color has changed, because different materials reflect and emit light differently. It explains why the dust size distribution has changed, because different layers of a comet can have different compositions and different mechanical properties. It explains why the shape has stretched and the tail is forking, because new vents are opening up on the nucleus, new jets are firing, and they're pointing in different directions than the previous ones. We're literally watching a new chapter of this comet's history being written in real time. A chapter that's been hidden inside it for billions of years, and now it's being exposed, layer by layer, as it's stripped away by the sun. But there's another piece to this puzzle, and it's subtle but important. When the teams recalculated the non-gravitational forces, these are the tiny extra pushes that the comet experiences from all this jetting activity, they found something interesting. The direction of that net push hasn't rotated much since the last update. Let me explain why that matters. The comet looks completely different. The character of the dust has changed, the shape of the coma has changed, the way it appears in every single wavelength has changed. But the overall thrust, the net effect of all those jets pushing on the nucleus, is still pointing in roughly the same direction it was before. What that tells us is that the vents are evolving, but they're not moving to completely different parts of the nucleus. The main active regions, the spots where jets are firing from, are still in roughly the same locations, but they're changing. Cracks are widening, layers are peeling back, deeper material is being exposed, vents are getting bigger or new ones are opening up right next to the old ones. But the general engine regions of this comet haven't migrated to totally new parts of the surface. Not yet, anyway. And that yet is doing a lot of heavy lifting here. Because the more layers you strip off, the more physical properties of the nucleus change. Its shape changes, its mass distribution changes, its structural integrity changes. Think about it this way. If the outer shell of this nucleus was relatively tough and uniform, like a protective coating, and the stuff underneath is looser or weaker or more volatile, then what we're seeing today might just be the beginning of something bigger. This isn't necessarily the final form of this comet. This might just be the early warning that something bigger is coming. We're entering a phase where the structural stability of the nucleus itself becomes questionable. We've already watched it transform visually. The question now is whether the interior can keep handling that transformation without something breaking. There are basically two ways this can go from here. Option 1, the comet smooths out into some new stable configuration. Maybe it stays elongated, maybe it keeps the double tail structure, maybe it continues throwing off this weird mix of different dust types from different sides, but it holds together. The activity eventually decreases as it moves away from the sun and cruises out of the solar system looking weird but intact. Option 2, each